Welcome to AI Papers in 10 minutes. I'm Nick, and today we're talking about practical algorithmic fairness. I'm sure you've heard that AI models aren't always unbiased, and that sometimes they unjustly favor one group of people over another. That's a pretty big issue, but unfortunately it's one where there's often lots of talk and sometimes not enough coding. Why is that? Well, there's a few reasons why there's a relatively little action. First of all, currently there's a lack of generally agreed upon practical methodologies to follow. And that forces everyone to put a very strong focus on only parts of the pipeline, in particular the gathering of what we think are representative datasets. And while data is super important, it has to be said that the current standard is still more or less fairness blind. When training models, we tend to select the one with the highest predictive accuracy, and we only deal with fairness once it hits us in the face. Today I'd like to discuss the paper Promoting Fairness Through Hyperparameter Optimization by Cruz, Solero, and Belem, who outline a practical bias reduction methodology we can use when training machine learning models, which integrates very easily in our existing pipelines and comes at almost no additional computational cost. Now, you might have noticed that all of these offers are associated to the company Feeds AI. Feeds AI is a company fighting financial crime with AI algorithms. That means that all of these offers really have skin in the game. One could even argue that fairness is part of their business model. When reading their paper, this is one of the first figures you come upon. And this figure illustrates the accuracy-fairness trade-off. All of the little blue dots you see here are trained AI models with different hyperparameter values. And on the x-axis, you see the model's predictive accuracy, and on the y-axis, the model's fairness score. Now, that's interesting, right? There's an explicit fairness score. Here on the right, in the red rectangle, we find model A, the model we would classically choose if we only look at accuracy. But now that we also have a fairness score, we actually notice that we could select model B, which is slightly less accurate than model A, but is much fairer. Now, that is the trade-off that we need to make when we take both accuracy and fairness into account. So how do we search through the space of all possible models? Well, the authors argue that we should focus on the models on this green line, which is the Pareto frontier, which means that, for example, for model B, it is impossible for me to move to a model which is fairer without that model also being less accurate, just as it is impossible to find a model which is more accurate, which isn't less fair. The authors say that we should promote fairness so that everyone training models takes fairness into account, but that at the same time, we don't want to force people to change their pipeline, because if we do, then it's very unlikely that they will do so, because we just want to train models the way we've always trained models, right? So why not just optimize? What if we just move from a single objective optimization problem, which is varying our hyperparameters to find the model with the highest accuracy, to a multi-objective optimization problem, where we vary the hyperparameters to find a model that makes the best trade-off between accuracy and fairness? For a neural network, for example, we already take into account batch size, dropout, and learning rate as hyperparameters. What if we introduce a new hyperparameter, which is called fairness importance, the weight we attribute to fairness versus accuracy? The authors argue that if we do this, it becomes easy to move to a multi-objective optimization approach when training AI algorithms. They say, here's just a little bit of math, that we want the max of this function, which takes the hyperparameters as input, and which actually is a function of both accuracy and fairness, and that we need to introduce this new hyperparameter alpha, which generates two weights, which is the trade-off that we were talking about. So if alpha, which varies between 0 and 1, is 0, we only care about fairness. If alpha is 1, we only care about accuracy. And so in order to find a model we want and move along the Pareto frontier, we can just vary alpha between 0 and 1. And we can evaluate our models on both fairness and predictive accuracy metrics on our holdout validation set. alpha is the trade-off. But how are we going to select these models? Do we just want to select them manually? I mean, we could, once we have a fairness and a predictive accuracy score. But the authors argue that it would be much cooler to have a heuristic for dynamically setting alpha. If we want to take that approach, then we need to know how we update alpha over time. For example, we could start with alpha at 0.5, saying we care equally about fairness and accuracy. But how do we update it over time? We somehow want this update to be proportional to the difference between fairness and accuracy. So that if we have a model which is super fair, but not at all accurate, we want it to move to a place where it is more accurate. And on the contrary, if we have a model that's super accurate, but not at all fair, we want it to move to a place in the hyperparameter space where it is more fair. So we want it to be proportional to this difference between the expected fairness and accuracy by some constant, which is greater than 0. And with a little bit of math and the constraints, where we know that this delta is between -1 and 1. And we also know that alpha is between 0 and 1. This is the weight that we attribute to fairness and accuracy. And we can actually show that alpha is 0.5 times this delta, fairness minus accuracy, plus 0.5. And we can use this formula to dynamically update alpha as we search through the hyperparameter space. The authors then continue to empirically illustrate that this approach works. And for this, they use the account opening fraud dataset, which is a financial dataset where you look at new bank accounts being opened and you need to determine whether or not the intent is fraudulent. And in this figure that they use to illustrate their results, I would like to focus on two result sets on Fairband and Fairband Auto. Fairband is a hyperparameter search algorithm in which the authors have set alpha a priori to be 0.5. And Fairband Auto is one where alpha is dynamically updated over time with the formula that we just showed. Now, Fairband here produces a set of models to choose from. But we see that Fairband Auto produces a much smaller set of models that are all more or less along the Pareto frontier. And that's pretty cool, because that means that if you have, for example, some minimum requirements of fairness, it's very easy to pick a model. You can just say, okay, I have 0.8 as a cutoff, for example. I need to use this model, right? Whereas for Fairband here, if you have to choose between these two models, it might not be so clear, or between these three models, it might not be so easy. So having proposed models along this Pareto frontier is a really useful feature. I think there's a couple of important takeaways from this paper. First of all, it shows that fairness-aware hyperparameter optimization is not only possible, but that it's effective. And that it doesn't come with any extra training cost, that it can be implemented in a really straightforward way. And in a way, that means that there's no more excuses. That every time we train a model, we should probably at least think about what it means for that model to be fair. And if we can actually quantify fairness in a score between 0 and 1. Because if we can, then we can integrate that into our optimization strategy. And we can actually, have a selection of models which make the trade-off in an intelligent and meaningful way. I hope you enjoyed this video. If you did, stay tuned for the next one, where we'll be looking at the Fairface database.